Photoelectric effect is a phenomenon whereby upon shining light onto a metal surface, electrons are released by the interaction of the energy from the light being transferred to the electron. Different observations from physicists about this effect, however, defied traditional understanding. For example, electrons could not be emitted no matter the intensity of the light if the frequency of the wave was less than that of a specific threshold. Traditionally, it was expected that the intensity of light would correlate to the energy of the light. Rather, as the intensity increased, more electrons would be released, but the energy of the electrons would be the same unless the frequency of the light was changed. That is, the kinetic energy of the electrons increased with increasing frequency of radiation. To conceptualize this, let's first look at an animation to demonstrate initial observations made by physicists studying the photoelectric effect. Here, we can see light being shone onto a metal surface, in this instance being sodium. If the wavelength of light is 400 nanometers and we increase the intensity of light to around 50%, we can now see electrons being emitted. And as it is further increased, more electrons are released. Now, leaving the intensity at 100% and moving the wavelength to 850 nanometers, no electrons are released. Only at about 480 nanometers do electrons begin to be released, but only very slowly, representing the energy of electrons. Changing the wavelength now to 100 nanometers, the electrons move very quickly, therefore representing more energy. So why does this occur? How can an increase in light intensity not affect the energy of electrons, but rather the wavelength and therefore frequency of the wave? This is where Einstein comes in. Einstein borrowed Planck's idea that light is made up of localized particles known as photons. These packets of energy have their own frequency. According to classical electromagnetic theory, the photoelectric effect was attributed to the transfer of energy from the light to an electron. This would mean that an alteration in intensity would result in changes to the rate of emission of electrons from the metal. But as we saw in the animation, this is not the case. Increased intensity only increases the amount of electrons being emitted, not the transfer of energy. Depending on the frequency of the wave, the energy of the light is different. This can be shown with the equation E equals hf, where E is equal to energy, h is equal to Planck's constant, and f is equal to the frequency of the light. That is, E is proportional to f, since h is a constant. When individual photons hit the metal surface, the energy is transferred to free electrons in the lattice, therefore giving it enough energy depending on the frequency threshold of that particular metal to escape the lattice. You might think, however, that if the intensity of the light increases, that one electron could be hit by two photons in quick succession. However, the chances of this are very small, and hence little to no cumulative effect occurs. Furthermore, the photon can only transfer all or none of its energy, as it cannot be split or transfer only half of its energy. Now, light can be understood as both a particle and a wave, which makes it difficult to understand the nature of light. In addition, measurements are only meaningful to a certain point since photons cannot be split. This proposed distance is known as Planck's length, or the shortest measurable distance, which relates to the generalized uncertainty principle, where the exact location of a particle cannot be determined. However, despite these minor conceptual problems, Einstein's quantum explanation of localized quanta, known as photons, has been extremely beneficial in our understanding of EM radiation and energy transfer, in particular the photoelectric effect.